Hi there and welcome. I'm Rebecca Weaver. We're going to finish up our discussion on curve sketching today. This is section 2.4, and let's get started by looking at a couple of examples, and then we'll give a summary as to what you're to do. So we're asked to sketch the graph of f of x equals x cubed minus 6x squared plus 12x minus 5. So I've graphed this function on Desmos. This is what I always do first. Whenever they ask me to do something about graphing, I graph it on my graphing calculator. I'm not going to take your graphing calculator away. You will still have to be able to use the derivatives to find your minimums and your maximums and tell me whether it's concave up, concave down, find critical points and points of inflection. But it really helps to have the graph right there in front of you or a good idea of what it is. So I would do that. So first off, we need to find the both the derivative, the first derivative, and the second derivative. So if we have the function f of x equals x cubed minus 6x squared plus 12x minus 5, then the first derivative, f prime of x, equals 3x squared minus 12x plus 12, using my power rule. To find the second derivative, I'll use the power rule again, take the derivative of my first derivative, and I'll get 6x minus 12. I'll need to find the maximums and minimums first, so that means I'll need to find the critical points. To do this, I'll set the first derivative equal to 0 and solve for x. When I factor that, I'll have 3x minus 6 times x minus 2. Factor that, I'll get that x equals 2 for both of these, which is pretty nice. So at x equals 2, I have a critical value. And I look at my graph to see if something is going on here, and I definitely see that there's a change going on at x equal 2. So I'm pretty happy about that answer. Now I'm going to look for the intercepts. I'm going to find the y-intercept by evaluating f as 0. It's my favorite one to find because I just plop a 0 in for x. When I do that, I get that f of 0 equals negative 5. So that's a y-intercept. I'll put that dot on my graph, the dot where x is 0, y is negative 5. I can go back just to see if at 0, negative 5 is on my graph, and indeed it is, so I'm pretty happy. So next, what I'm going to do is I'm going to find any x-intercepts. Not quite as easy, so what I need to do is set this thing equal to 0 and see if I have any x-intercepts. Well, let me just go ahead and look, whoops, and see, do I have an x-intercept? Yeah, I do. It's some sort of fraction there in between 0 and 1. I don't quite know what it is, but um, the equation doesn't really factor and the quadratic formula can't help us because this is a cubic. And if we attempt to use the rational roots theorem from algebra, in doing so, we find that there are no rational roots for my x-intercepts. So if there is an x-intercept, it's an irrational number. So we can do a couple of things in order to find that x-intercept, one of which is to use our calculator, another of which is to use a table of values. First, I'll show you how to use the calculator. Okay, we're going to use our calculator to find the intercepts. It's another way to do it. To do this, what we're going to do is press y equals. It's right there underneath your graphing screen. Then you'll enter the function into y1. You'll hit graph. You'll press the second or the blue button of the older calculators. This is a yellow button. And then you'll press calc. Now calc is written right above the trace button, and you'll see it's written in blue or yellow depending on what color button you had. You'll select number 2, which is to find the 0. You'll use your left and right arrow keys to place the selector on the left side of the intercept. You'll press enter. Use your left-right arrow keys to place the selector on the right side of the intercept and press enter. Now this selector looks like a little flower or a little spider or something like that. You'll see him. Just move your arrows left and right until you find him. The calculator would then like for you to guess or give an estimate. I don't usually guess because that's the calculator's job, so I just tell him to do it by pressing enter, and then he'll give you what he believes to be is that interception point or that 0. Another way you could do it would be to say, well, I know it's somewhere in between 0 and 1, and just calculate some values. So if I plug in 0.54 for the y, I get negative 0.11. If I plug in 0.55, I get the y is negative 0.05. If I plug in 0.56, I'll get 0.01. At this point, I know it's somewhere in between 0.55 and 0.56. Closer to 0.56 probably, because that's where it would be 0. 0.57 you can calculate it if you want to, but you can see that that's going up because that's 0.08, so that one I wouldn't even need. Notice that the y values corresponding to x equals 0.54 and x equal to 0.55 are below the x-axis, and the y values corresponding to x equals 0.56 and x equal to 0.57 are above the x-axis because they're positive. Therefore, in between 0.55 and x equal to 0.56, there must be an x-intercept. Now, for the sake of brevity, we'll just take the x equals 0.56 because we know it's close for our x-intercept, since out of the four values above, it has the y value that's closest to 0. Therefore, the point of our x-intercept is 0.56, 0. I can't graph any closer than that anyway. So now we're going to sketch a graph of the function, or we're going to sketch that point, and then we're going to do some other points as well. So looking at that second derivative at x equal 2, we find that we know that it equals 0. Now, we don't know anything about the graph at x equal 2. However, the test for inflection points suggests that we have an inflection point at x equal 2. First, let's verify indeed we have an inflection point at x equal 2. If this proves to be not the case, we're going to use a similar method using the first derivative to see if we have a relative extremum at x equal 2. We're going to look at the left and the right-hand limits of f double prime of x and see if the values of the second derivative are oppositely signed as x approaches 2. Looking at this table of values, I see that indeed on one side of 2, on the left side of 2, the 1.99 and the 1.99, all of those values are negative. That's really all I care about. On the right-hand side of 2, 2.1, 2.01, those values are positive. From the values of f double prime of x in the table, we find that as x approaches 2, the second derivative not only has a limit of 0, but the values of the function to the left of 2 are negative. Also, the values of the function to the right of x equal 2 remain positive. Therefore, by definition, f of x has an inflection point at x equal 2. Since the graph of f of x is concave down to the left of x equal 2 and concave up to the right of x equal 2. Notice, x equal 2 was the only candidate for generating a relative extremum. Therefore, there are no relative extremum. We will now find the y-coordinate for the inflection point. And how we do that was we just plug in x equal 2 to our function, and we find that the y value there is 3, so the only inflection point is at 2, 3. Here's our graph, and I went ahead and put the Desmos graph on here too, just to show you how scaling makes something look a little different. You'll notice the graph that I have here sitting in the very center is the numbers go 1, 3, 5. They're very spread out. Here that I did on Desmos, I've stretched out the y so it goes from 0 to 10 instead of 0 to 20. So it makes it look different, but it's still the same graph. So looking at f of x, f prime of x, and f double prime of x, f of x yields information about where things are on a graph. F prime of x yields information about slope on a graph. F double prime of x yields information about concavity on the graph. So let's look at another example. We're going to look at graphs with asymptotes. In this example, we're to sketch the graph of f of x equals 12 over x plus 3x plus 1 for all x greater than 0. So of course I had Desmos graph this for me so that I could look at it. And I see that Desmos is telling me I do have an asymptote right here at x equals 0. See that big old sucker right there? I mean, that's like straight up and down there. And that has to do with the fact that if x is 0, this thing is undefined because of that 0 that would exist in that denominator there. The function's only valid for x greater than 0, so I didn't bother graphing anything further than that. I need to find the first and the second derivative, so taking those derivatives, f prime of x is negative 12 over x squared plus 3. F double prime is 24 over x cubed. I need to find the critical point, so I'll set the first derivative equal to 0 and solve for x. In doing so, I find that x equals, it actually equals positive negative 2 going through this algebra. However, in my domain, I don't have an x equal negative 2 because they restricted my domain to x greater than 0. So I would say that x equal 2 is our only critical value. So writing that down in words, we exclude the case x equal negative 2 since this is outside of our specified domain. The graph has a horizontal tangent at 2, f of 2, which is 2, 13. Since f double prime of 2 equals 3, which is greater than 0, the graph is concave up at x equal 2. And by the second derivative test, 2, 13 is a relative minimum. In fact, f double prime is positive for all positive x. Therefore, the graph is concave up at all points. Before sketching the graph, notice that as x approaches 0, the term 12 over x in the formula for f of x is dominant. That is, this term becomes arbitrarily large, whereas the terms 3x plus 1 contribute to a diminishing proportion to the function value as x approaches 0. So that means 12 over x really takes over. He becomes big. Thus, f of x has the y-axis as an asymptote. For large values of x, the term 3x is dominant. That's why we see it shoot off kind of in a straight line. The value of f of x is only slightly larger than 3x since the terms 12 over x plus 1 has decreasing significance as x becomes arbitrarily large. So as x becomes really, really big, 1 doesn't matter and 12 over a really big number doesn't matter because that's getting closer to 0. So that's really like a 1. That is, the graph of f of x is slightly above the graph of y equals 3x plus 1. As x increases, the graph of f of x has the line y equal 3x plus 1 as an asymptote. So here is our graph. Same graph, just different scaling. One in Desmos, one when I just drew it here on the in the middle and put points on it. So you can notice that y equal 3x plus 1. See how that main function is approaching that line, just a little slightly above it. All right, so next we'll do a summary of each of these curve sketching techniques. Step number 1, you need to compute f prime of x and f double prime of x. We're going to need the first and second derivatives. Step 2, find all relative extreme points. I actually graph it using my graphing calculator as step 2, but technically they don't know that I'm doing that. A, find the critical values and the critical points. Set f prime of x equal to 0 and solve for x. Suppose that x equal a is a solution or a critical value. Substitute x equal a into f of x to find f of a. Plot the critical point, always plot the critical points, and draw a small horizontal tangent line through the point so that you'll know that it flattens out there. Now compute f double prime of a. We're going to do the second derivative test. If f double prime of a is greater than 0, the curve has a relative minimum at x equal a. Draw a small concave arc with f of a as its lowest point. If f double prime of a is less than 0, the curve has a relative maximum at x equal a. I would draw a small concave down arc with a, f of a as its peak. Now, next I would do the first derivative test. If f double prime of a equals 0, examine f prime of x to the left and the right of x equal a to determine if the function changes from increasing to decreasing or vice versa. If a relative extreme point is indicated, draw an appropriate arc, as in parts 1 and 2. repeating the preceding steps for each solution or each critical point to f prime of x equals 0. Number 3, you're going to find all of the inflection points of f of x. To do this, you will set f double prime of x equal to 0 and solve for x. Suppose that x equal b is a solution. Compute f of b and plot the point b, f of b. Test the concavity of f of x to the left and the right of b. If the concavity changes at x equal b, then the point b, f of b is an inflection point. Consider other properties of the function and complete the sketch. If f of x is defined at x equals 0, the y-intercept is 0, f of 0. Just plot that point. Does the partial sketch suggest that there are x-intercepts? Now, if so, they are found by setting f of x equal to 0 and solve for x. Solving only in easy cases or when a problem essentially requires you to calculate the x-intercepts. Observe where f of x is defined. Sometimes the function is given only for restricted values of x. Don't plot it if they restrict the domain. Sometimes the formula for f of x is meaningless for certain values of x. You're also going to look for asymptotes. Examine the formula for f of x. If some terms become insignificant as x gets large, and if the rest of the formula gives the equation of a straight line, then that straight line is an asymptote. Suppose that there's some point A such that f of x is defined for x near A, but not at A. For example, 1 over x at x equals 0. If x gets arbitrarily large in the positive or negative sense as x approaches A, the vertical line x equal A is an asymptote for the graph. So you'll want to find those. So look in the denominator where you might get a 0. And then you're going to complete your sketch. Now that's all I have for your curve sketching techniques. One thing that I would do is utilize that graphing calculator where you can. All right, if you have any questions, be sure and email me, rweaver10@alaska.edu. And you have a wonderful day. Bye now.